This is our final project presentation. Our final project title is Image Completion with LoRa. This is our outline. Image completion contains image in painting and image out painting, which is a task to fill the missing content in a specific region of an image. To address this task, we aim to utilize diffusion models, known for their ability to generate diverse and seamless images. However, due to the inherent randomness in the inference process, the generated images will be unrealistic. Therefore, we propose training LoRa weights to guide the diffusion model. With the guidance of a few reference images, the LoRa weights enhance the model's ability to generate high quality and realistic images. LoRa is a technique designed to efficiently adapt large pre-trained models to specific tasks by introducing a low-rank decomposition of the adaptation parameters. This allows for effective fine-tuning with a relatively small number of additional parameters. Take this image as example. The pre-trained weight has shape d times d. They freeze the pre-trained weights and introduced adapted matrix delta W, which can be decomposed into b times a. The shape of b times a maintains the d times d shape. However, since r is much smaller than d, the trainable weight is significantly reduced from d times d to 2 times d times r. This is our pipeline. We inject LoRa weights into both text encoder and UNet in the diffusion model. Since the image will do cross-attention with the text embedding and self-attention to itself, the UNet will take the noise latent of an image randomly selected from the reference images and original masked images. And it also takes a latent of the mask randomly generated mask and the mask image latent. And it also takes the text embedding as input. Specifically, the text prompt is a fixed sentence, a photo of SKS, where SKS is a rare token used to represent this scene. The loss function is similar to all the diffusion model-based loss, where it aims to predict the noise added on the clear image. During the inference process, the target image, the mask, and a random generated Gaussian noise are combined as the input. The fixed text prompt, a photo of SKS, is used as a condition. Then, we use the adapted model to fill the desired region of the target image, resulting in a faithful, high-quality output. However, since the inference process is still stochastic, generated images might come with undesired distortion and artifacts. Therefore, we generate a batch of images first and rank them by light glue, a transformer-based keypoint matching algorithm, against one of the selected reference images. The image with the highest correspondence is selected as our final result. This is our experiment results. The second column is the target images. The third column is the ground truth images. The fourth and fifth columns are generated images with or without fine-tune. And the semi-transparent region is the unmasked area of the target image. As shown in the figure, after fine-tuning, the generated image is more similar to the original target image. The evaluation matrix also support our argument, whether considering pixel space metrics PSNR SSIM or feature space matrices such as LPIPs, FID. The fine-tuned model outperformed the baseline model. This suggests that after fine-tuning, the generated images are more realistic and high quality. We have also done some ablation study. Given the reference images on the left, best result column, which has the most key point matched to the selected reference image in the batch, is more faithful to the reference image compared to the worst result column, which has the least key point matched. For example, in the worst result column, the top row displayed a mismatch in the number of boats, and the shape of the building on the right side is incorrect. In the bottom row, there are incorrect number of car toys on the right side. We have also tried to train multiple scenes at once, and we get decent results. The adjusted input training data consists of 3 distinct scenes, each represented by a differently colored square, paired with its corresponding text prompt. As a consequence, 3 distinct rare text tokens, SKS, XYZ, and T at T, will guide the LoRa to generate their associated scenes. However, our methods still have some limitations. Our approach fails to reconstruct high-fidelity images in complex scenes containing numerous objects with varied arrangements. Also, the fine-tuned model relies on the base pre-trained model's image prior. It also fails to handle cases that are challenging for the base model, such as text or human faces, as shown in the bottom row in this figure.